All right, physics guys, welcome to distance learning. We're going to spend the next few weeks anyway doing screencasts. I'll be doing screencasts. You'll be watching screencasts, and hopefully this works for you. We'll have distance learning Google Hangout office hours if you need to ask questions on Tuesdays and Thursdays from 9 a.m. to 10 a.m. I'll send out a Google Hangout link if you want to contact me, or if you want to work at the same time on a problem, and we could either do it with phone or video and walk through things. So that's available from 9 to 10. I'll send the link out. But what I want to do in this first screencast is just kind of review a little bit of circular motion since we've had a week off, and then we'll go through a problem or two on worksheet 1 and 2 to try and get you grounded back to what we were doing before we had our break there. So remember that circular motion at constant speed is what we're talking about. And if you remember in class, I had a little rubber stopper at the end of a string, and I was spinning it over the top of my head. So I'm trying to give you that as an example again, because you can hopefully picture that. And what I want to kind of focus on is this is a top view of the stopper going around in a circle. So you're looking down on the top of it. And if you notice here, every instant, I'm going to try to show you here. Here's the velocity pointing tangentially to the path. And what I'm saying here is the path is going around this way. So it's rotating in that direction, which would be counterclockwise. And you can see the velocity is always tangent to the path at any moment. But the net force, the thing that causes it to go in a circle, is the tension, which is always tension in the string that's acting on the stopper. So my object of interest is the stopper. That's the thing that's moving in a circle. The unbalanced force that acts on it that keeps it going in a circle, in this case, is that tension force. And I show it always pointed towards the center of the circle, regardless of which position it's in. It's always pointed towards the center there. And we talked about different forces that can cause circular motion. Tension was one of them. But objects don't want to go in a circle by nature. Objects want to move in a straight line at constant speed or stay at rest if they're already at rest. The only thing that makes this thing go in a circle is that unbalanced tension force towards the center. So in circular motion, you've got this constant tug of war at every instant. And what I mean by that is you've got the velocity that points tangentially to the path of the object. Tangentially means it is touching that path at one point, that circle. And if I was able to actually slide this over, move everything, you can see the path of the object is tangent at that instant. But it doesn't go in that path for more than an instant because the tension pulls it towards the center. So you got this tension force that makes it turn. So up at the top, velocity to the left, tension force towards the center. You notice they're always at a 90-degree angle to one another. That's an important feature of circular motion. Down here at the bottom of the page, I've said circular motion is at constant speed. It has another name. It's called uniform circular motion. So uniform circular motion, or sometimes abbreviated UCM, is circular motion at the same speed, uniform being constant speed. Remember that Newton's second law still applies, so net force is equal to mass times acceleration. That's still just as true in circular motion as it was in linear motion. The only difference in circular motion is that net force is always pointed towards the center of the circle. Okay? And we give it a special name. We call it a centripetal force, which means that the acceleration is a centripetal acceleration, because if you remember from Newton's second law, the object always accelerates in the direction of the net force. It can't be any other way. Doesn't always move in the direction of the net force, but it always accelerates in the direction of the net force. That means its velocity is changing in the direction of the net force. If you remember before we had our break, we derived an expression for centripetal acceleration, and we figured out from our data from the simulated lab that we did that the acceleration is equal to the square of the speed divided by the radius of the circle. So that means that if I substitute this in for the centripetal acceleration in our Newton's second law expression, we have the centripetal force is equal to mass times the square of speed divided by the radius. And even though I use this term F with a subscript C to denote that it's a center-seeking force, a centripetal force, it's still the net force. It just has a special name because it's circular motion. Okay, so that's a little review of what we had done in the couple of days before the break. Let's kind of apply that to a couple problems. And the first one I'm looking at is from Worksheet 1. We did the first 2 or 3 problems in class on Thursday before we left. I asked you to do 4, 5, and 6 yourself, so that's going to be due on Monday by the end of the day. Number 5 I'm going to look at real quick to kind of get you grounded again on how to approach these problems. Part A is pretty straightforward. That's just a force diagram for a roller coaster on a flat track. I'm going to let you do that yourself. Part B's more relevant to what we're talking about. Part A and Part B are both important, but they have you draw it on a flat surface first to contrast the force diagram for an object on a flat surface with the force diagram for an object that is undergoing some sort of circular motion, which is in Part B. So what we're going to do, I'm going to zoom in on Part B here, and we're going to focus on that. We're going to draw a force diagram from the side for a roller coaster car moving up and over the top of a hill. And they ask, are the forces perpendicular to the track balanced? If they're unbalanced, explain why there is a net force and in which direction the force acts. So this looks like, even though it's not drawn as a circle, this point is kind of a circular, that portion of the track is kind of a circle with a radius. I tried to draw a little radius there of R. So I'm going to draw a force diagram over to the right here of the car. And I know there's 2 forces acting on it. There's a gravitational force straight down. That's equal to the mass of the object times the gravitational field strength, 10 newtons per kilogram. And I know that that is always pointed straight down, regardless of if the car is at the top of the hill, bottom of a hill, wherever it is. The Earth is always pulling us straight towards the center. The other force is the normal force that acts on it. So there's a normal force of this surface pushing up. So I'm going to draw the normal force here. And notice how I'm drawing it a little bit shorter than the gravitational force. Why am I drawing it shorter? Because I know this object here of interest is in circular motion. That means it is got an unbalanced force acting on it. And that means that that unbalanced force, since it's in circular motion, is pointing towards the center of the circle. Well, the center of the circle is right here. I only have 2 forces acting on it. I've got the downward force of gravity and the upward normal force. And if I know that the unbalanced force has to be pointed down, that means FG's got to be bigger than the normal force. So I'm going to let you answer in words if the forces are balanced, because I just talked through that. I want you to put it in your own words. If they're unbalanced, explain why there is a net force. Think about the motion of the car at this instant and in which direction the force acts. Okay? Okay, now I'm going to jump to worksheet number 2. This is the first question on worksheet 2, and our favorite car, a Jeep Wrangler, is moving with constant speed, but it's not moving with constant velocity. So there's that. Seems like a paradox. How can something move with constant speed but not constant velocity? I'm going to let you answer that because we've talked about that a few times at this point. Draw a qualitative motion map. Okay, you guys know what a motion map is. That's a dot representing the position of the object for every second. So it's not just for that one location. A motion map is over the course of its journey here, and they're most interested in where it is as it's moving along. I'm just going to draw evenly spaced dots. And why are they evenly spaced? Because it's moving with constant speed. So every second, it's covering the same amount of distance. But by drawing the motion map, it's going to help us see why its velocity is not constant. So the arrows are all pointing in the direction of motion at that instant. And if you notice, my arrows are constantly changing direction until it gets on the flat. So the fact that the arrows are moving in different directions every instant, this arrow points in a different direction than this one, should lead you to understand why this isn't constant velocity. It doesn't say to draw acceleration arrows for this motion map. If I did draw acceleration arrows, you can tell where they would be pointed, towards the center of the circle. So I would have little acceleration arrows that are constantly changing in direction, pointed towards the center of the circle. And the acceleration isn't changing, it's the magnitude of it, it's just the direction of it is changing. So the blue arrows represent velocity, the red arrows represent acceleration. I'll let you answer this question here. Okay, so let's look at part D down here. Construct a qualitative force diagram for the Jeep. Qualitative meaning, not quantitative. We're just going to show the lengths of each force that's appropriate and the length of the arrow that represents the magnitude of that force. For the Jeep, at the instant it's at the bottom of the valley. Okay, so that would be as it's shown right here. The instant it's at the bottom of the valley. Are the forces balanced? Justify the relative sizes of the forces. Okay, so off to the side here. You'll do it down here in part D. All right, I'm just doing it off to the side to kind of show you what's going on. I know I've got the Earth's force down. I'll call it Fg, the mass of the object times g. And you might say to yourself, well, he's moving horizontally at this instant. Okay, so at this instant, his velocity, it shows the arrow there pointed straight to the right. So you might think, okay, he's moving horizontally at that instant, so it must be a balanced force diagram. But the velocity is changing every single instant because he's in circular motion. He's come down the hill, now he's headed back up to the hill, up the other side of the circle. It just happens that at this instant he's at the bottom. He's undergoing circular motion though. So the unbalanced force has to point towards the center of this circle up here. So I know that if I'm going to have an unbalanced force pointed up from where he is, my upward force has to be longer than my downward force. So I'm going to draw my normal force pointed straight up to the center like that. So I know that my normal force is larger than this force here, is larger than this force here. So I have an unbalanced force pointed up, this being a little bit larger than that one. Okay. Hang on. Let's move on to part E. Same problem. If the Jeep's speed is 30 meters per second, its mass is 1,300 kilograms, and the radius of the valley is 20 meters, calculate the magnitude of the unbalanced force acting on the Jeep. Okay, so they're giving us some numbers now. Let's write down everything we know. I know the Jeep's speed is 30 meters per second. That's v, even though we've used that for velocity in the past. For speed, we use the same letter, v. It just doesn't have a direction. The mass is 1,300 kilograms. The radius of the valley, 20 meters. And they want us to calculate the unbalanced or net force, which I know in this case is also, because it's moving in a circle, the centripetal force. Same thing. Well, I have an equation for the centripetal force that looks like this. Centripetal acceleration is the v squared over the r. I've got a v over here. I've got my r right here. I've got my mass right here. Just fill in the numbers over here, and this is more a math problem than it is a physics problem. So you didn't have to do a whole lot of thought process to get that answer. But now you have to draw a quantitative force diagram for the Jeep at the bottom of the valley. This is going to require a little bit more thought. Now that you know FC, let's go back to our force diagram of the Jeep. We had FG pointed down. We had the normal force longer and pointed up. This number that you're going to calculate right here is the centripetal force, which is also known as the net force. Well, neither one of these is the net force. These are individual forces that are acting on the Jeep. You know the net force is the sum of all those forces added together, and it's whatever's left over. Well, one of these is pointed up and one's pointed down. So the net force is the difference between those two. So you take the larger force, the normal force pointed up, subtract the smaller force, the gravitational force pointed down, you get the net force. And now you can actually solve for, you know what this is, based on the mass of the object up here. You can figure out what the normal force is based on knowing the net force from the above calculation and knowing the FG from M times G. Okay, I hope this helps. Finish up worksheet number 2 for Tuesday. If you have questions, I'll send the Google Hangout for office hours on Tuesday and Thursday from 9 a.m. to 10 a.m. And stay safe and stay home, guys. Take care.